today's class we'll be talking about equilibria. And we're going to use a representative reaction that's described in your textbook. The reaction of dinitrogen tetroxide, which breaks down into nitrogen dioxide. And the nitrogen dioxide is a brown gas that you can often see in smoggy cities where, especially in the summertime, because the equilibrium shifts towards the right, you'll see an orange pall hanging over a city. Very often it's because of the presence of nitrogen dioxide in the air. Now when the temperature drops, the reaction tends to shift to the left, and you'll see that because the boiling point of the substance is 21.5, it can also become a liquid at those lower temperatures. And if you go to sub-zero temperatures, it can actually turn into a solid. If you take a liquid nitrogen bath and dip a sealed tube of this gas, you'll see the gas go from brown to clear to essentially sublimate into a form of a deposit inside the tube of this solid form of the chemical. I drew a couple of Lewis structures to try to understand what the structure looks like, and you see when you draw the single molecule, you get a Lewis structure with a single unpaired electron in the nitrogen atom, which would actually give a nitrogen atom more than an octet. So then I drew one of the canonical structures having a formal charge on oxygen and a positive charge on nitrogen, which would be more in keeping with the fact that nitrogen does not easily accommodate expanded octets. In fact, will not normally accommodate expanded octets. So this is perhaps a more accurate Lewis structure. But to form this structure, which is a proposed Lewis structure for N2O4 dinitrogen tetroxide, you have to envision a bond forming between the nitrogen atoms, which would mean that now again we have another expanded octet for nitrogen, so I redrew another structure where the oxygen atoms take on a negative charge, a positive charge, a negative charge on the oxygen, and the nitrogen takes on a positive charge, and it loses its expanded octet. So probably the reality is somewhere between these two structures, and also gives the explanation for why the molecule has a somewhat unstable structure. At any rate, this reaction occurs continuously, and we have a forward reaction represented by the arrow going this way, and we have a reverse reaction represented by the arrow going that way. The rate for the forward reaction is given by a rate constant F, K sub F, to symbolize that it's the rate constant for the forward reaction, times the concentration of dinitrogen tetroxide. The rate for the reverse reaction is given by K sub R times the concentration of nitrogen dioxide raised to the power of 2. They put this power of 2 because it's based on the stoichiometric coefficients of the balanced reaction. So whenever you have a stoichiometry of 2 to 1, for example, then the rate constant for that reaction will have to be raised to the power of 2. And as regards the final equilibrium, if you set the two reactions equal to each other, as would happen when the reaction is at equilibrium, the rates of the forward and the reverse reaction are going to be the same. So what I've done is I've grouped the constants and I've grouped the chemicals to the other side, and we get a value Kf over Kr, which we call K equilibrium, and that is the equilibrium constant. Note that at equilibrium the concentrations stop changing because both forward and reverse reactions are occurring at the same rate. However, both reactions continue. Even though you don't see a chemical reaction taking place, in fact, both reactions are still taking place. They're just in opposite directions. So the net effect is 0. The next thing we should understand about equilibrium constants is the law of mass action. The law of mass action expresses the relationship between concentrations of products and reactants present at equilibrium, using the balanced equation, of course. So in the conceptual equation where product A and B combine to form reactants A and B combine to form products D and E, where lowercase a, b, d, and e are the stoichiometric coefficients, then the value of the rate constant, of the equilibrium constant for that reaction, Kc, is going to be based on the concentration of products divided by the concentration of reactants, and where the stoichiometric coefficients are going to become powers. So A will be raised to the power of A, B will be raised to the power of B, and so on, where these lowercase letters are the stoichiometric coefficients of the balanced reaction. And the uppercase letters represent the concentrations of the chemicals involved. The equilibrium constant expression depends only on the stoichiometry of the reaction and not on its mechanism. The value of the equilibrium constant depends only on two things as well. The reaction, different reactions have different equilibrium constants, and the temperature. Varying the temperature can shift the equilibrium of the reaction. As an example of these two things being applied, we have ozone turning into oxygen gas. Both of them are gases, and Kc, the equilibrium constant for that reaction, would be given by the concentration of products divided by the concentration of reactants, where the coefficients are used as powers. So the oxygen concentration raised to the power of 3 divided by the ozone concentration raised to the power of 2 will give you the equilibrium constant for that reaction. Normally units are not listed for values of Kc. When we're dealing with gases, we use Kp as the equilibrium constant because we're using partial pressures. So for the general reaction, again, A plus B gives D plus E. The value of Kp will be based on the partial pressures of each one of the gases involved, and again, the stoichiometric coefficients will become powers. And it is possible to convert between Kc and Kp by using this conversion factor. Kp is equal to Kc times RT raised to the power of delta N, where delta N is the difference in the number of moles between a product versus the number of moles of reactant. So delta N, the power that we raise RT to, is moles of gaseous product minus moles of gaseous reactant. Therefore, if the delta N is equal to 0, in other words, if there's no change in the number of moles between the products and the reactants, then Kp is going to equal to Kc. And for the value of R, we use 0.08206, the value of the gas constant that we normally use for when the units are liter atmospheres per Kelvin mole. That is, if we're using pressures, partial pressures are listed in atmospheres, then we use R for the value of liter atmospheres per Kelvin mole. An example. Suppose we had Kc equal to 4.08 times 10 to the minus 3 at a temperature of 1000 Kelvin for the reaction where sulfur trioxide turns into sulfur dioxide. What is the value of Kp? So we plug in the values of RT, and the delta N is going to be 1 because there are 3 moles. When you form sulfur dioxide from sulfur trioxide, you get a mole of oxygen. So there's 3 moles of gas on the right-hand side of the equation, and there's only 2 moles of gas on the left-hand side of the equation. So products minus reactants, 3 minus 2 gives you 1. Change in the number of moles is 1. Therefore, we raise RT to the power of 1 when you multiply it by Kc. Plug in all the values, and we get a value of Kp is equal to 0.3348, which rounds off to 0.335. Continuing with considerations about the value of K. When the value of K is greater than 1, it means that the ratio of products over reactants is large. So that means the products are predominating at equilibrium. When K is a lot less than 1, then the reactants are predominating at equilibrium. The equilibrium constant expression for a reaction written in one direction is also the reciprocal of the one written in the reverse direction. So again, going back to the reaction we had at the beginning, nitrogen tetroxide, dinitrogen tetroxide turns into nitrogen dioxide. Here's the Kc value for that reaction, and it works out to 0.212. If you were to write the reaction backwards, you would now have to write the Kc expression upside down, the way you wrote it the first time, and therefore the numerical value is going to be the reciprocal, which is 4.72. 3 sort of rules arise from some considerations and observations of the use of the equilibrium constant. The first is that K for the reverse reaction is the reciprocal for the forward reaction. 2, if a reaction is multiplied by a number, then its equilibrium constant is raised by the same number. And lastly, the equilibrium constant for a reaction made up of 2 separate reactions is the product of the 2 equilibrium constants. And if there are 3 reactions, it's the product of the 3 equilibrium constants, etc.